Let's talk a little bit about accelerating ions. Ions are just charged particles. So a proton is an ion, and an electron would be an ion. So it would be like, an iron +3 atom, right? Okay. And so if we drop a proton near the +12 volt side, right here this is, right? It's going to, if this space is evacuated, you have to have like a vacuum, a very good vacuum. It would accelerate uninhibited until it hit this plate. Okay, and the basic concept here is that change in voltage is equal to change in potential energy over charge. So therefore, the change in potential energy of that proton would just be the change in voltage times its charge, right? And when it goes from here to here, it would turn its potential energy into kinetic energy, right? So the basic idea behind all accelerated ion problems is that the change in voltage times the charge equals 1/2 mv squared. Okay, that's the basic thing. Now in the data packet this doesn't exist, but they do have this formula. I'm not sure, it might be EV or something like that, right? What they're saying here is voltage times charge. They don't even bother to put the change in voltage there, right? Times this must be the electron charge, right? Is 1/2 mv squared. Well, that's exactly what's going on there. Here's a proton with a charge of E. It's plus E, right? Plus 1.602 times 10 to the minus 19th coulombs, right? That's what's exactly going on. So this is like a formula for accelerating protons or electrons. But if it's something like an alpha particle that has two charges, well, then we got to put a 2 in there or something like that. So you're far better off understanding that this is just potential energy from that formula turning into kinetic energy. Okay, so let's look at this problem here. I'm going to hit the right arrow there, and that brings up this is our charge, that's our mass, right? And I'll just go ahead and use the formula in the data packet. VE is 1/2 mv squared. So this is our potential energy, right? That's 12 volts or 12 joules per coulomb, and then times 1.602 E minus 19th coulombs, right, is 1/2. And then a proton doesn't have much mass compared to a baseball, but it's actually pretty massive. E minus 27 kilograms times V squared, right? So my velocity will be this 2 times this divided by this. It'll be the square root of that, right? So square root of 2 times 12 times 1.602 e to the minus 19th divided by 1.673 e to the minus 27, right parenthesis, and I get 47938 meters per second, okay, as my velocity, or we'd round it like that. Now, I just want to raise a red flag here. 12 volts is not very many volts, okay? What if we accelerated through, I don't know, 500,000 volts? Well, if we did that, we could actually calculate a velocity faster than the speed of light, or 1,000,000 volts. Let's make it 1,000,000 volts, right? We could get a velocity faster than the speed of light. Well, the speed of light is 3.00 times 10 to the 8th meters per second. So for now, I really want you to just sort of think about this. If you ever get a speed that's anywhere close to that, this formula here is going to break down. This assumes that the mass stays constant. And as these particles approach the speed of light, the mass definitely does not stay constant. Okay, it dilates, it gets bigger, because energy has mass, right? E equals mc squared. And so as you gain enough kinetic energy, you will also gain mass, okay? So the next thing I want to talk about is something called an electron volt, which is actually a unit of energy. If you recall, change in potential energy is just change in voltage times charge, right? So voltage times charge is electron energy, right? So an electron volt is defined as the energy of one electron charge moved through 1 volt. Now, if I move a proton through 12 volts, it would have 12 electron volts of energy. And if I moved a proton through 100 volts, it would have 100 electron volts of energy. Or let's mix it up here. What if I move 3 electron charges through 5 volts? I would have 15 electron volts, right? So it's just basically we're talking about charge in units of electron charges and voltage in units of voltage, okay? Let's try another one here. An electron accelerated through 12 volts has 12 electron volts of energy, right? And then 1 electron volt is actually equal to 1.602 times 10 to the minus 19th joules. Well, that's because it's 1 volt times 1 electron charge, right? 10 to the minus 19th coulombs, right? So you can literally translate electron volts into joules. They're not very much. They're not very many joules, right? Okay. And then, you know, let's think about this. Other particles are a little more complicated. An alpha particle is 2 protons, 2 neutrons. Okay. If you neutrons have no charge, right? But these have 2 electron charges, right? Well, 2 electron charges through 12 volts. 12 volts, right, is 24 electron volts. Okay. Now finally, before we go, I just want to throw this idea at you. Okay. Let's go to Google Chrome here and look at our data packet. This is the elementary charge, right? And they leave off the 2. It gives me a rash. Okay. Electron rest mass is there. They give it in kilograms. But notice that they're also giving it in millions of electron volts. That MeV means millions of electron volts. What they're saying is that if you turn an electron into energy, that's how much energy in electron volts it would have. Now, let's go back to our thing. Okay, an electron is 0.511 million electron volts, right? That means it's 511,000 electron volts of energy, right? Now, let's accelerate an electron through 300,000 volts. My college had a particle accelerator that did this. Actually, I think it was only 150,000, but it makes a better story. Okay, now, here's the cool thing. Notice that the thing has this much energy as mass. It's gaining this much kinetic energy. Its mass would now be 811,000 electron volts. It now would have much more mass. It would be, what, 60% more massive than it was before, right? Okay, we can measure that mass. It really does happen, right? So that's what we're talking about. You know, if we significantly change this mass, this is our rest mass, this is energy mass. Okay, that's why in particle physics we talk about the energy content in electron volts, because we're using particle accelerators. Okay, all right. More on that when we get to chapter 26.